Hi everybody, welcome back to the Feynman Technique. I've got a good one for you today. This is going to be kind of a long video, even though I will be leaving some of the more, the busy work steps out. There's still quite a lot going on here. We're going to evaluate this integral, and it is not easy. So the first thing we're going to do is we are going to rewrite it as the imaginary part of a complex logarithm. So just remember that the imaginary part of of the natural log of a complex number a plus bi is just arctangent b over a. So we could rewrite this integral as the imaginary part of the integral from 0 to pi of the natural log. Well, here, I'll show you. Um, if we let our b equal 1 plus cosine x and our a equal 1, we get that the imaginary part of the natural log of 1 plus, this is our b, which is 1 plus cosine x, times I is just going to be arctangent of b, again, which is 1 plus cosine x over a, which is just 1. And that's going to give us our original integral. So let's define a function of t like this. It's just going to be the integral from 0 to pi of the natural log of, and now you'll see what I did is I replaced this I with a t. So now it's just a function of t. So we define a function of t, and notice that clearly f at t is equal to 0 is going to give us 0. And if we set t equal to the imaginary unit I, and then take the imaginary part, we have the imaginary part of f at I is the imaginary part of this integral right here. And that is our original I. All right. So next, let's go ahead and differentiate f of t with respect to t using the Leibniz rule for differentiation under the integral sign, and which says all we have to do is pass this inside the integral sign as a partial derivative, then take the partial derivative with respect to t of the integrand, and we have f prime of t. So that's f prime of t. And we can rewrite that a little bit. If you use some algebraic manipulation, you can see that this is equal to this. Again, I'm not going to show those steps. So we can rewrite our f prime of t as just pi over t minus 1 over t times this integral right here. And this integral is in a form that I have covered before. So we'll be able to plug that into a formula and get the answer without actually having to do much integration. The formula that I'm talking about is this. I will link to the where I derived this formula in the description, but it's very useful. It just says this. Okay, so you'll notice that we have that form right here, where our a is 1 plus t and our b is just t. So we can plug those in and get the following. Again, set a equal to 1 plus t and b equal to t. And we end up getting this. So this integral is just pi over the square root of 1 plus 2t. So our whole f prime of t is, again, I didn't show this, but that's just going to be pi natural log t. So, no, I'm sorry. No, that's the next step. So our f prime of t is pi over t minus pi over t square root of 1 plus 2t. All right, so now we need to integrate f prime of t to get f of t, but that's going to introduce a constant of integration. Again, I did not show the steps for this. This can be, you can integrate this using just standard calculus 1 integration techniques. You'll have to use, I believe it's just u substitution and partial fraction decomposition, but if you do that, you can get this. The antiderivative of this evaluates to this after simplification. So now we need to figure out our constant of integration c, and we can do that by taking the limit as t goes to 0, because we know that f at 0 is equal to 0. So we take the limit as t goes to 0 to find our, and set it equal to 0 to find our constant of integration. All right, I'm not going to show the work here, but if you take the limit as t goes to 0 of this expression right here, it goes to 2. So this thing right in here is just pi natural log 2 plus c is equal to 0. So our constant of integration is negative pi natural log 2. So plugging that in, and we have our final expression for f of t. And you might think that, oh, great, well, now all we have to do is plug in I. Yeah, well, we have to do that and then find the imaginary part of that. So now comes the hard part. Let's evaluate our expression f of t at t is equal to I and extract the imaginary part. So again, I is equal to this. All right, so let's try to, well, since we already know how to take the imaginary part of a complex logarithm, why don't we try to write this expression inside the natural logarithm as a plus bi? All right, so that's what we're going to try to do. Let's start simplifying this expression inside the natural log. So what we can do is first we multiply the top and the bottom by this numerator right here, and we get this. And then if you do it all out, and you'll end up getting this. Just do the work, and you end up getting this expression right here. All right. So what can we do now? Well, we can actually FOIL this out. If we FOIL this out, what this whole thing whittles down to is just this. Okay, so now we have this thing inside the natural log is just equal to this. All right, we're doing a little bit better now. We still haven't gotten it completely into the form of a plus bi. We need to simplify this square root right here. All right, so we can put this into polar form, which is just going to be the magnitude times e to the argument. I forget exactly what it says, but basically the magnitude you just find. All you do is well, it's going to be r times e to the I theta, right? That's the polar form of this. So we just take its magnitude, that's r, so that's going to be the square root of 5. And then e to the I theta, that's whatever angle that point makes with the origin. So the angle would be the arctangent of 2 over 1. If you create a right triangle and you can see that the angle there is going to be the inverse tangent of 2 over 1. So we have this expression can be written as square root of 5 times e to the I arctangent of 2. All right. But we need to take its square root. So taking its square root, we end up getting this. Okay? So square root of 2i plus 1 is just equal to this. All right, so we can plug that in to here and then separate the real and imaginary parts. All right, so plugging that in, we find that expression inside the natural log is just this. And we know how to take the imaginary part of the logarithm of a complex number. It just gives us the arctangent of b over a. So this is going to give us the arctangent of our b, which is what's in front of the I, or after the I right here. So that's arctangent of this over this. All right. Well, still, we can do a lot better than that. Let's recall that, let's use the half angle identities for cosine and sine. So if we plug arctangent 2 over 2 into the half angle identity, we can see that this is equal to this, and this is equal to this. And also, the cosine of arctangent 2, you can just make a right triangle, setting the tangent of arctangent 2 is obviously equal to 2. Build a right triangle, and you can see that the cosine of arctangent 2 is going to be 1 over the square root of 5. So we can plug that in. We can plug in 1 over square root of 5 in for cosine arctangent 2. And then finally we have this. And that would be good enough. I mean, I'd say most people would probably stop there, but you can actually get a much nicer expression for the thing inside the arctangent. I'm not going to show the work, but that can actually be reduced to just this. So after simplification, the final answer is pi times the arctangent of the square root of square root of 5 minus 1 over 2. All right, guys, I hope you enjoyed that, and we'll see you next time.